Next up, we're going to be talking about position compare. Position compare is a very high speed, up to 100 megahertz sampling frequency with some nominal output rise time. That it's an output that is toggling, triggering, typically based off of the motor position. So, if you want to record data or turn on a laser, generally, if you want to interface the PMAC with some other device and make sure you trigger something on the other device at a very precise moment, the position compare and the related EQU output pin is going to be generally what you'll want to use. The sampling rate is the encoder sampling rate, because you can't go any faster than that. You're going to get your encoder position data at whatever clock speed you get it in, again up to 100 megahertz, and as soon as the hardware sees the value in that encoder register equal to or greater than, or toggling over basically, a pre-computed value, it will turn an output pin high to 5 volts, and then it'll drop it low again at another pre-computed time. It doesn't go through the backplane bus to the CPU. It's entirely the hardware and the ICs on the exis card itself. So very, very slight delays, if any delays at all. But you do need to do a little bit of work to set it up to calculate it, because it's looking at the raw encoder values. So you need to make sure that the value you're comparing is a raw encoder value. These are the relevant commands for it. Quickly stepping through them. You have gate3.chan.equ, which is just a way to query the current value of the EQU output. You have EQU write, which writes a value to it. EQU enable, which determines whether or not the EQU output will trigger based on its own encoder counter or that of channel 0 for the same IC. I'll explain what that means in a little bit, but basically it determines where the signal to turn the EQU output on is coming from. You have EQU out mask. Generally, you only want to look at a single channel. Typically, you're going to have EQU coming from the axis assigned to motor 3. You want to look at motor 3's flags, and so you'll only mask it to look at that channel. But theoretically, you might want that pulse to turn on when this motor hits a trigger and that motor hits a trigger, and we get a flag over here. If you have a more complex triggering event, you can use EQU out mask to determine what it is that's actually going to cause it to trigger. EQU out pole for polarity determines whether you're looking for high or low true. Then the important ones, you have CompA, Comp B, which are the actual points at which this will trigger on and off. It should be noted we call them CompA and Comp B just because they have to be distinguished. For the purposes of this, we're going to always have Comp A be the on pulse and Comp B be the off pulse. However, in PMAC, they're completely indistinguishable. It doesn't matter whether you hit B first or A first, you'll still get the same event. Either one of them just causes the output pin to toggle. And then you have Comp Add if you want to set up a repeating pulse, so on for 20 counts and then off for 1 inch of axis travel, and then on again. So you just want to take quick samples at a larger interval. You can set up Comp Add and it'll automatically increment your Comp A and Comp B registers as appropriate. So EQU write is actually bits 6 and 7 of gate3.chan.control. It's a 2-bit element there. You can access it either way. However, EQU writes can be the easier way to access it. And it's made up of a forcing bit and a writing bit. The most significant bit is the writing bit, which is to say when you trigger it to write to the EQU output, whatever value is in the most significant bit of EQU write will be the value that actually gets sent to the EQU output. And the lower bit is the forcing bit. Whenever the lower bit goes high, so whenever EQU write has an odd value set to it, it will then set the most significant, the writing bit, to EQU out. So just to go through a bit of an example on the board here to show you what that actually means, we have the EQU actual value. Then I'm going to say we have our EQU write. So EQU write, if I put a value of 0 in here, that translates to a writing bit, as I call it, of 0 and a forcing bit of 0. If this is the case, if EQU starts out at a value of 0, it's going to remain at a value of 0. Because, first of all, our writing bit is 0, but that doesn't even matter. Our forcing bit is 0, which means we are not going to force any value into EQU. We're not changing the value of EQU. Now, if we instead put $3 here, that's 1, 1. Have Anthony right now. I don't know if you guys want to trade off or not. Okay. Sorry about that, guys. If you were to set a value of 3 here instead, we have our writing bit is high and our forcing bit is high. That means since this forcing bit is high, we are in fact going to write to the EQU. And because this has a value of 1, we're going to write that value of 1 into the EQU output. Now, let's say instead I wanted to go with a value of 1. That's going to be 0, 1 here. In this case, we have our writing bit is 0, so we're trying to write a value of 0. And our forcing bit is 1, which means we are in fact actually going to write that. So I'm now going to reset this back to a low value of 0. And then the last case, if we have a value of 2, we have 1, 0. In this case, we are trying to write a value of 1, but our forcing bit is 0, so we're not actually going to write it. So we're going to retain the same value, in this case, 0. It might be better if I replace these two with x's, because what will actually happen in these two cases here is whatever the previous value of EQU was, it will not change, it will remain at what it had been. So in order to change the value of the EQU, we set EQU right to either $1 or $3, and that will in fact force it. Setting it to either of the other two values will not change the value. You're welcome to try this on your boxes right now. If you want, you can either run through in this order I wrote here so you can see a change and a change back, or you're welcome to run through them in this order here. If you stick gate30.chan0.EQU in your watch window, which I recommend you do anyways because you'll be watching that a lot in this section. If you set EQU right to those 4 values, you should see the EQU only toggle on the third one, which I'm going to do here just so you can see also. Going to add .EQU here. So if I issue $1, we see the actual EQU value does not change at all. If I issue $3, it does change. And if you issue any even number at all, it will never change because the forcing bit is still low. But if you issue an odd number, it will set the value. So that's how to manually change the EQU output, which is useful both when you're setting up your system because you want to make sure that your laser, your sample, your data acquisition card, your whatever it is, you want to make sure that signal starts out either high or low depending on what you want so that it's pulsing the right direction. But it can also be useful if you don't need the high speed. You could always theoretically just write a quick PLC, have it toggle that bit high or low as you want, and you can use it for just debugging, making sure the output's toggling. You can use it just for a very quick one so you don't have to do the work of calculating into encoder counts. But the meat of this section really is having it do it for you. So, in order to have PMAC do it, you do need to do everything in encoder values. We've given a composite equation here, basically, that will let you calculate from your axis values, which are the PA in this second equation here. From your axis values, you can calculate your motor values, and then from your motor values, you can calculate your encoder values. And it all comes down to this equation here. Basically, you take that axis value, multiply it by any axis scale factor you may have, and then you add any axis offsets you may have, and that'll be your combined motor value. Then with your motor value, similarly, you add your homing position to it, your homing offset. You, again, factor that by your motor scale factor, and then you multiply that by a factor of 4096. That's simply because the data in the encoder register, there's not a decimal place in it, so the first however many bits of it are fractional counts. So if you get a motor value of 5 motor counts, you need to scale that up by 4096, such that that 5 is effectively 5 whole counts in your encoder register, rather than being 5 4096ths of a count. Now, a couple things to note here. As I said, the encoder position has 12 bits of fractional resolution, so you always need to scale that. Most of these parameters are existing PMAX structures. Your motor home position is motor_x.homePos. Your position loop scale factor is motor.pos scale factor, pos_sf. And then your axis scale factor and axis offset. Those you can pretty much look up what they are from a table. Your axis offset will be motor.coord SF32. That will automatically look at the coordinate system in which that motor is assigned. And every number, every index for that possible brackets there, that 32, corresponds to a different axis, 0 through 31. We have the table of the first 9 of them down here. If that motor controls your A axis, you're going to look at 0. If it controls your B axis, you're going to look at 1, etc. up through 31, because there's 32 possible axes. So if you put 32 in there, rather than getting the scale factor of any given axis, that will just gather the total offset. Because again, remember, your axis definition might be motor 1 corresponds to 1500x plus 5000. Coord scale factor 32 is going to be that 5000. Then from that, again, your axis scale factor is going to be coord scale factor with whatever number corresponding to your axis. A through C are 0 through 2, UVW are 3, 4, 5, XYZ are 6, 7, 8, and then it starts up again. AA is going to be 9, BB is going to be 10, going on through the alphabet, ignoring those 3 that we're skipping. And that would be how you determine that. So I suppose a comprehensive one would actually have possibly multiple different scale factors all being included into our equation, but the stuff we're going to be doing is just going to be quick linear, motor 1 controls the x-axis kind of stuff, so we can only deal with one scale factor at a time. Then we finally have the axis position, which is your user input, and your encoder position, which is going to be your output. So rather than trying to run through all the calculations every single time, we decided to try and automate this a little bit for you guys. So I want you all to copy this code here into a new file, put it in your global includes folder, global includes and libraries, and just name it whatever you'd like, possibly position compare reference or something. Just to step through what this does, the first thing it does is it's defining easier ways to call all of those parameters from the previous slide. I should note, this assumes you're using motor 1 for everything. If you're using a different motor, you will need to change a couple of indices as appropriate. Namely, motor 1 home pause pointing to motor 1 home position. You change that to motor whatever you're using. And then your CompA, Comp B, and Comp add here, you will change as appropriate the channel number from 0 to whatever channel corresponds to the motor you're going to use. So throughout this example, we're going to be calling the variable names on the left side there rather than the full structures on the right. And then this equation right here, these 2 lines in a subprogram, they perform the calculation on the previous slide. One slight difference between what's on this slide and the previous page was that in addition to the equation, we're performing a modulo operation. We're taking our motor position scaled into encoder counts before that 4096 scale factor and performing a modulo with 2 to the 20th. That is in a PMAC 3 IC card like the Accessory 24 E3s. It rolls over the encoder position register in the position compare stuff. It rolls over after 20 bits. For PMAC2, so an accessory 24 E2A or below, it rolls over at 24 bits, but the scale factor 4096 changes a little bit also. So even though it may look like 24E3 is lower resolution, it is higher resolution than the previous one was, but you can't necessarily see it from this slide. But again, the purpose of this modulo of 2 to the 20th is just to deal with the fact that the actual encoder register in the PMAC is going to roll over. So if you end up with a value outside of that range of 2 to the 20th, you'll never see that value come in from the encoder. So by now everyone probably should have copied this or modified it as appropriate and stuck it in their PMAC. So let's go into a quick application. For this, we're going to have a 13-inch lead screw with a pitot tube attached to it to take some pressure measurements. However, it's going to travel along 10 or 12 inches of that 13-inch lead screw. We only care about the data it gets in a narrower range from it. So we decided that for this sample, we're going to use the EQU output such that the EQU output's going to go high when we're in that range. That's going to trigger some third-party data acquisition software or possibly another device or something like that that will actually start gathering the data from the pitot tube in that range. Just to go over the specs of the system, we have the instrument itself is centered on a stage that's 3 inches wide. The stage is on that 13-inch lead screw that has a gear ratio of 1 revolution of the screw corresponds to 1 inch, and 2,000 counts of the encoder correspond to 1 revolution. So 2,000 counts of the motor is 1 inch of travel. And we want it to turn on at 3.5 inches and off at 8 inches. So just to convert this into math that PMAC will understand, well, let's first actually go through the steps of this. First thing we'll do is we'll convert those numbers to numbers that PMAC will understand. We're going to feed in the data to it. Then we're going to convert our axis positions ultimately to encoder positions. We're going to set the EQU output to a low level to begin with because we want it to turn high in the range. We're then going to set up our position compare A and compare B registers. We're going to turn off our auto increment, and then we're just going to move the motor through the range. So motor 1 is going to be our x-axis. To guarantee that we get the data across the entire range, we're going to have the x-axis move well beyond the end of the range. Sometimes if you have it move to the endpoint of your compare register, as the motor, there's some noise on the line or the motor dithers a little bit or something like that, you may end up crossing that boundary to turn position compare on and off repeatedly, and you may end up getting a whole bunch of noisy data at the end of it, rather than if you move just past it altogether, you know that it's not going to keep turning position compare on and off the whole time. And this is the first slide that you guys are going to copy and download next. We're setting up in coordinate system 1. Motor 1 is going to be our x-axis. And in this program, all we're doing is calculating our position compare A and B values using that subprogram from the previous slide. We're setting those in the proper registers, and then we're just going to move the motor out to 10 inches and back. So with this, we should expect to see we have a plot of position versus time and also EQ output. We should expect TM's 5,000, TA is 100. So a move time of 5.1 seconds. What am I doing? Then it will stay there for a dwell of 500, 5.6 seconds, and then come down at another 5.1 seconds, so 10.7 seconds. And as we cross 3.5 and 8 were the numbers that we decided on. We should see the EQU output turn high, stay high, drop low, and then do roughly the same thing as we go backwards through it. So this is as good of a time as any. I'm going to ask for your attention really fast and just show you how to do something in the IDE window. Because now we're dealing with a kinematic axis, or not much of kinematics, admittedly, it's one-to-one, but we're dealing with axes rather than motors. We want to change our position window to actually show the units that we're dealing with. So, in the IDE, I'm going to come over here to my position window, and I'm going to right-click just somewhere in the blue of the window, and go Properties, Control, Motor Specific. This will bring up a new dialog box for any given motor. And I'm going to stay on motor 1 because that's the motor I'm going to be using for this. The next step would be to set up the encoder position. Now, if you look back at our system, we have a 3-inch wide platform here. And I'm going to say we're homing to a home switch that's probably going to trigger off one of the edge of the stage, either the first edge or the second edge of the stage itself. So in order for our instrument to be centered on that home switch rather than the edge of the platform centered on the home switch, we need to include an offset of 1.5 inches or 3,000 counts. So I'm going to set my motor.home offset equal to -3,000 in this case. And now that I've set my home offset, it's safe to just home the motor outright, and it should, if we were using the actual system, move such that the instrument is centered on our home switch. The next step is setting up that initial EQU level. Now we want our EQU output to be turned off to be low when we're at our home position, so we're going to write a value of $1, which again sets the forcing bit high and the writing bit low, so we write a value of 0 to our EQU output with that. And you can just issue this in your terminal window. For right now, it's a bit unnecessary because your EQ outputs most likely already are low, but just to be safe, it's always better off to do this and make sure it's set up and it's where you want it to be. Next, we need to set up our position compare locations. Because of some shortcutting we did a little while ago that I'll go back to mention in a second, all we need to do is set CompA pause to 3.5 and CompB pause to 8. Now the reason we get away with doing that is because back here in our subprogram, we already declared global variables CompA pause and CompB pause, and our absolute encoder position calculation subprogram is a function that accepts an input and gives an output to it. So we're just going to pass the value of CompA pause into that subprogram, and we'll get back a result that is stored in CompA pause encoder, which here we're setting equal to motor 1 CompA. Going back to the subprogram, we see that it was written such that it accepts an input and gives an output. So, now that we've set these two values here, we do need to disable CompAdd. So this one will just manually set gate3.chan.compadd equal to 0. What this does is now, even if CompAdd, you can think of it like this, CompAdd is always on. It's just a matter of now it adds a value of 0 to your CompA and CompB, so effectively it does nothing. So setting it to 0 disables your auto increment. And then the last thing you need to do, once your motor is homed, your home offset's put into it, and your CompA and CompB are stored in those two values, just run the motion program. Issue AND1, B1R, or whatever coordinate system you chose to put this in, whatever program number you chose to use for it, and running it, you should end up with a plot that is very hard to see on the projector. But it should look similar to this graph I drew up here, where it increases over a span roughly equal to 5 seconds, a little bit over it, turning the EQ output high in the middle of that, and then waits a half second, then decreases again over a span of 5.1 seconds with the EQ output changing in the middle of it. So your plot, if you plot it, should look something like this one here. That's how you set it up for a single pulse. Okay, so just to recap a little bit, we all just set it up so that as the motor reached, or as the axis reached 3.5 inches and 8 inches away from the home position, our EQ output turned high, setting it to a value of 1, which outputs 5 volts on the EQU pin. And then as it got to 8 inches, it turned off and back. For this next example, though, we're going to go with a repeating pattern. The pattern for this one will repeat every 2 inches, in which it will turn on, the pulse will stay on for 1/4 inch, turn off, and remain that way for another 1 3/4. So at 1 inch it turns on, 1 1/4 turns off, 3 inches on, 3 1/4 off, 5 on, 5 1/4 off, and on from there. So in order to do this, we home our motors first of all, but each pulse will still be bounded by CompA and Comp B, using Comp add to increment the pulses as we travel along. Whenever we reach Comp A, Comp B will be incremented. And whenever we reach Comp B, Comp A will get incremented. This means that basically if you start off bounded by your Comp A and Comp B registers, one ahead of you and one behind you, as you move across, every time you hit one, the other one will leapfrog over you, and you'll end up still in between the two of them as they perpetually play catch up with one another. So, as this explains it, motor 1, that red dot there, is starting in between Comp A, the green bar, and Comp B, the blue bar. And motor A is going to just continually move forward in the x-axis. Now, at a certain point, motor A, or motor 1, is going to hit our Comp B location here. And when it does, our Comp A bar is going to move all the way over to here. So as we cross the border, the opposite one will move so that we're still in between the two of them. Then as we hit what's now Comp A, which is now ahead of our motor, as we cross Comp A, Comp B will be incremented such that now Comp B is ahead of us, and on from there. So if we start off in between Comp A and Comp B, we will always remain inside of Comp A and Comp B as long as our Comp add is large enough to increment them beyond one another. So the process for this is basically the exact same as the process was before. We set up our kinematics for axes and determine the motion, in this case moving out 10 inches and back. We convert our axis position to motor position and our motor position to encoder position, so we know what the raw encoder value is at which we want the EQU to toggle. We set our default position compare output to 0 by writing EQU right to a value of $1. We set up our Comp A and Comp B for the first pulse, and that will change a tiny bit from the last example. We actually set our Comp add to a value now because we're going to be using it, and then we just move the motor along. So because those first 3 steps are the exact same, I'm going to jump straight into step 4. The first thing to notice, though, is I kind of snuck it in when I was explaining it. The motor needs to begin bounded by Comp A and Comp B, which means if you want it to pulse on at 1 inch and off at 1 1/4 inch, either you need to start your motor in between 1 and 1 1/4 inches, or you need to do something a little bit weird with one of the boundaries. I'm going to draw it up here. We eventually want, with our motor starting out at 0, the pulse on here and off here, which means our motor is going to start out here, and we know we want 1 pulse here and 1 pulse there. But again, we need to start out in between the two of them. So what we're actually going to do is decrement this pulse by our Comp add register such that it's all the way back here. What that will do is, as we move the motor along, as it hits the first point that turns the EQ output on, this will be incremented and it will end up back where we want it to be. So, for a case like this, we're going to set our Comp A position still equal to 1 inch, where we want the EQU output to turn on, but we're going to set our comp B position equal to negative 0.75, which is 1.25 minus 2 inches. That way, as we reach the 1 inch mark, our comp B will be incremented and end up where we actually want to see it. If you issue these two lines here, when we run the motion program, it will put them into the right registers and move for you. Now, the next thing we need to do is we need to actually set up our comp add. Now, the comp add calculation on the surface is the exact same as the comp A and comp B calculations. But if you actually look at it carefully, there is a slight difference, which is our comp add is going to be an incremental number. That means while all the scale factors are the same, we don't want the home offset included, we don't want the axis offset included, we don't want any of the offsets, we just want the scale factors. So I made another subprogram here. The other one was absolute encoder position compare. This is incremental encoder position compare. I want you guys all to copy this couple lines of code into the same file where you have your abs enc pos calc and just paste this below it. So we'll use this one pretty much exclusively to calculate that comp add. And all it is, if you compare it to the other one, it's the exact same calculation, except it cut out the home offset and it cut out the axis offset. What? It's low, it's dying? Okay. There's another... Okay. Do you know how to change it? You have to pull it off the tripod. Okay, I'll show you. Okay, so I'm going to assume that everyone's stuck this into theirs. Now, this code we added on because we're using both this and the other one. But we now need to modify our actual motion program so that it uses both equations. So we need to add 3 lines of code to our motion program. First, we need to add another global variable, comp add dist, in addition to comp A pos and comp B pos. We'll be using that to actually input our comp add values. Then we need to add another call so that we call the incremental encoder position calc so that we can actually calculate what our comp add is. And then we need to add another line that sets motor 1 comp add equal to that calculated value. So you're welcome to either just add those 3 selected lines into your existing program, or you can copy this entire program and add it in addition to the other one, however you'd like to do it. This does have a different name. It's now Auto-Increment Example Prog, so you can keep both of them if you want to be able to refer between different versions. There will be a third one example after this one. So if everyone has added these 3 lines to their program, and we have set our auto-increment value to 2, all that should be left is running our program. So and 1 B auto-increment example prog run would be one way to start off the motion program. And if you're watching that gate.chan.equ in your watch window, you should see motion that now looks more like this, which, again, I apologize, is hard to see on the projector. But if I'm going to come over here, basically what it is as the motor moves up along this path here, we see our EQ output spike high, tiny bit, then high again, then high and high and high, 5 times in the upswing, 5 times on the downswing at 1, 3, 5, 7, and 9 inches. So we already talked about how the motor has to be bounded by your comp A and comp B at all times. But sometimes you're going to have a scenario where that's just not feasible. For instance, in this case here, for whatever reason, I don't want that first pulse at 1 inch to 1 1/4 inches. I want to start my pattern at 3 inches out. In order to do that, I would need to, if I decrement the comp B register by 2 inches, it's still at 1 1/4, which means my motor's over here, but the pulses I want are those ones. out at 3 and 3.25, I explicitly do not want this pulse at all. So in order to set up my CompA and Comp B so that I'm in between them, I would need my Comp B to be all the way back here. And then the issue is, as soon as I hit 3, my Comp B would still only increment one time. It would end up right here, and I'd be outside of my register, so I wouldn't actually get the pattern at all. Now, if I'm not doing auto-incrementing, this also isn't an issue, because I just set up wherever I want my one pulse. Doesn't matter if I'm anywhere near there or not. It'll turn on, it'll turn off, and everything will be done. But in order to handle this, there's a couple of different approaches you can take. One of them, which is how you would have had to do it in Turbo, is to basically have a PLC or something else that watches the motor position, and as soon as it determines that you're inside of that range here, from here to here, or from here to here I guess I should say, you have that PLC set up the position compare stuff for you. That way you're always in between your CompA and your Comp B registers as long as your CompA and Comp B registers are set up. You just don't set it up until you are in between them. But for Power PMAC, we've added in a new functionality. Basically, we've set it up such that if you set a couple of things, one thing in particular, in a specific order, PMAC will automatically skip the first increment. So, rather than having to worry about this decrementing the second pulse so that it's before you, so when you get to the first pulse it'll increment to ahead of you, you don't need to set up any of that. You don't need to worry about this at all. All you do is set up Comp A at 3, Comp B at 3.25, and PMAC will know when you hit your very first pulse to do absolutely nothing, and then when you hit your second pulse, continue on as if you're using Comp Add. So when you get to the second pulse, 3 will jump out to 5. When you get to 5, 3.25 will jump out to 5.25. So in order to do that, this explains more or less what I just said. In order to do this, we've reordered the steps slightly. Now, for step 3, you set up your Comp A and Comp B. Step 4, you set up your Comp Add. But then after you've set up your Comp A, your Comp B, and your Comp Add, after you've set those up, then you write to the EQU write register. If PMAC detects that the EQU write has been changed or that the EQU value has been manually overwritten, even if you write it to its own current value, more recently than the Comp A, Comp B, or Comp Add registers were changed, it will know that you're trying to skip that first pulse. So all you do is you make sure that after you set up all of your parameters, you rewrite to that Comp write, the EQU write, and you're golden. That does also mean, though, conversely, if you don't want it to skip that first pulse for whatever reason, if you were using a case where it's fine to have your motor in between the two, you need to make sure that after you set up your Comp A and Comp B, you don't touch your EQU level. You don't write to EQU write. So we're going to do very similarly to before. Set up Comp A pause equal to 3, Comp B pause equal to 3.25, where we want our pulse to turn on or off. We're going to set our Comp Add distance to 2, same value as it had been for the previous example, but we're just going to rewrite to that value right now to make sure it's set properly. And then after we've done that, we need to set EQU write. It doesn't matter whether we set it to 1 or 3. We can set it to either of the two. What matters is that we actually are forcing and writing to our EQU value. So because our motion program is the one that's setting the Comp A and Comp B, we need to edit this into our motion program. So now we set our Comp A, Comp B, Comp Add with these 3 lines here, and then we're adding another line to it below those, gate30.chan0.EQU write equals $1. If we add this line in here, PMAC will not increment on that first pulse. Make sure you issue dwells everywhere to make sure everything takes. PMAC will not increment on that first pulse, and when you run the motion program, the plot should look something like this, which, again, I know you can't see, but it is in the handouts I gave you all. Basically, it's the exact same plot as the previous one, with the exception of there is no pulse at 1 inches. It just stays at a low value, pulses up at 3 inches, 5 inches, 7 inches, 9 inches, and then levels out at 10, and then it travels back. Now, if you're looking carefully at this, you'll notice one of the slight limitations. You have to look very carefully to see it, I know. But if you're looking carefully at this, you'll notice one of the slight limitations, which is as we travel backwards from 10 back to 0, the EQU output will turn high when we reach 1.25 and will turn off when we reach 1. So PMAC doesn't remember that you had wanted to skip that. It doesn't remember that you'd wanted to start your pattern at 3. All PMAC knows is that you told it you wanted to skip the first increment, and you did, and now every other increment, forwards or backwards, will pulse. One way to handle this would be to have a PLC that writes EQU right at given points to stop the incrementation, or simply make sure that when you're moving your motors, make sure you don't move a second time through any of the points you don't want to gather.